Okay, so today we're going to talk about the distorted Fourier transform. Okay, so in order to motivate, this topic, let's recall how we dealt with the stability of zero problem. Well, to deal with the stability of zero problem, we looked at the linearized problem around zero, and the linearized problem around zero is just the flat Schrödinger equation. So that's around zero. And that's for NLS, but obviously for KDV, you take the Airy equation. Okay, so now what if you want to linearize around a soliton psi? So you linearize around a soliton psi. Then what's going to come out is actually something a bit complicated. So let me write, this is the problem we will study, but the actual problem you want to study if you linearize around the soliton psi also involves a term with a u bar, which complicates things further. So for us, we'll be happy with studying this case, which has all the conceptual questions coming up, but which saves a bit of the technical difficulties. So these are the linearized problems around zero and around the soliton. So around zero, what did we used two things. First, we used decay estimates or Strichartz estimates. And second, we used the fact that, if you remember, for the cubic Schrödinger equation, we used the representation of the solution in Fourier space, which ultimately is linked to the fact that the Fourier transform diagonalizes the Laplacian. So in other words, if I take dx squared f hat of xi, this is minus xi squared f hat of xi, as we all know, right? So in other words, if you conjugate multiplication by xi squared with the Fourier transform, what you get is the Laplacian. So in other words, taking the Fourier transform provides a basis in which the Laplacian operator is diagonal. And so we'd like to get these two same elements, so one decay or Strichartz estimates on the one hand, and a diagonal basis on the other, for this new linear problem. And the key element in getting that is the distorted Fourier transform. And I should say it's also called the Weil Kodaira Titchmarsh theory. So it's just the theory of one-dimensional Schrödinger operators. And it can be generalized in a rather straightforward way to Sturm-Liouville operators. Okay, so that's the plan for today. Let's do it. Unless you have any question. Okay, so what we are after is diagonalizing the one-dimensional Schrödinger operator. Which of course is self-adjoint if you have the right functional setup. So that's, if you want, a particular case of the spectral theorem. So the spectral theorem. Let's review a few things about the spectral theorem. Okay, so in finite dimension, if you take M, a real symmetric matrix, you can write it as M is the sum j equals 1 to d of the lambda j ej cross ej. So that's just the projector on the vector ej multiplied by the vector ej. So here ej is an orthonormal basis, and lambda j are real numbers. Okay, so we all know that from our undergraduate years. So now let's move on to infinite dimension. So in infinite dimension, the easier case, so dimension d equals infinity, the easier case is when you have only discrete spectrum, and that's the case, for instance, if M is compact. So M is a compact operator on a Hilbert space which is self-adjoint. Then you can also write M as the sum. This time the sum goes to infinity. And the lambda j, the only difference is that now they go to 0 as j goes to infinity. Okay, so we want something yet more general. We want an operator that is infinite dimensional, but that is not compact. If you think of the Schrödinger operator, it's certainly not going to be compact on L2. So what's the general version of the spectral theorem we'll use? Let me state it now.
Sorry, I have one question on these compact operators.
Yes.
Do you use that your operator is self-joint? Because otherwise it's not really clear to me. So I think in the general case you normally have these singular values where you have different EJ.
That's right, yes. It is self-adjoint, yeah.
Okay, so you assume it's a self-joint compact operator.
Yeah. Okay, so right. So how about in the general case? So now we take M. So now general case. So M is a possibly unbounded self-adjoint operator on a Hilbert space. Then one way of stating the spectral theorem is that M can be written as the integral of lambda dE lambda. The integral is over R, and these are a projection or this is a projection valued measure. In other words, the integral between A and B of dE lambda is EB minus EA, where these things are projections. Okay, so of course here there is much that I'm leaving under the carpet. You know, what is an unbounded operator, what is a self-adjoint operator, and how to make proper sense of this rather formal equality. But I think we can manipulate these things as though everything was working you know, reasonably, and then if you want to know more, you can open a textbook on spectral theory, like the book by Gerhard Teschel is really very nice, and it covers all these things, including one-dimensional Schrödinger operators. Okay, so in a way, this theorem sort of answers the question: if you take M to be the Schrödinger operator that we're interested in, so M is minus dx squared plus v, then you know this gives an appropriate way of diagonalizing the operator. Of course, I should insist that this is the analog of what we wrote earlier. So earlier, the integral was replaced by a sum, but there was always real numbers and projections. And the fact that we need an integral has to do with the possible presence of continuous spectrum. Okay, so in a way this answers the problem, but sort of this doesn't tell us anything about what these projections are and how we can effectively compute them. So it's also important to have a statement about, you know, how these projection operators arise, which is part of the proof of this theorem. So the way to define these projection operators is to go through the resolvent. So the resolvent R is R of xi, M minus xi inverse if the real part of xi is not 0, then this is a bounded operator because M is self-adjoint. Okay, and then Stone's formula gives you a means of computing the projection valued measure. So it's saying that dE lambda, or maybe I should denote it, yeah, dE lambda is good. dE lambda is 1 over 2 pi I R of lambda plus I0 minus R of lambda minus I0. And so here, so this should be understood as the limit as epsilon goes to 0 of R of lambda plus I epsilon. And if you have minus, minus I epsilon. So once again, part of the theorem is that this makes sense, and this does define a projection. And maybe the way to make sense of this equality is to integrate both sides. So if I integrate this between a and b, I get the integral between a and b of this. Okay, so Stone's formula gives us a means of computing the spectral resolution of the operator M. And now our program is going to be to apply this to Schrödinger operators and see what the projections look like.
I'm sorry, I have one short question.
Yeah.
In the definition of the resultant, you said that you want the real part of psi to be non-zero.
Yes.
But I think you mean the imaginary part, right? Because M is self-adjoint.
Oh, yeah, of course. Thank you. It's the imaginary part of Xi, which is non-zero, right? So, roughly speaking, M has, or at least heuristically, M has a real spectrum. So as long as Xi doesn't have zero imaginary part, it's not in the spectrum, and therefore everything is fine. Thank you. Okay, so now we're going to try and apply this idea to Schrödinger operators. Okay, so now we want to apply Stone's formula to a Schrödinger operator of the form minus dx squared plus v. Okay, so we need to find the resolvent. So the resolvent will be denoted R sub v of Xi, and so it's a linear operator, so we can represent it through its kernel x, y, right? By which I mean that if you apply Rv of Xi to f, what you get is Rv of Xi of xy, f of y, dy, and that's at x, sorry. Okay, so we'd like to compute this object, the resolvent, and to compute it, what we need to solve in the sense of distributions is, so we want to solve minus dx squared plus v applied to Rv of Xi of xy is delta of x minus y, right? So, and sorry, here there is minus Xi. Right, so with the resolvent is the fundamental solution associated to the linear operator minus dx squared plus v minus xi. So you see that if y y is different from x, then all we are actually solving is minus dx squared plus v minus xi applied to a certain function f equals 0. So that's just really an ODE problem. It's an ODE problem, and it's a second order linear ODE, so it has a space of solutions which is a linear space of solutions of dimension 2, and so we need to investigate it. And then if y equals x, there is this jump condition that in the first derivative, which when you take two derivatives will give rise to this delta. Okay.
You're noting the same way the resolvent and the green function associated with the operator. RP of psi is the green function and the operator resolvent.
Oh yeah. So I'm slightly abusing notations by writing RV of xi for the operator and its kernel. Thank you for the clarification. Yes, right. So RV of xi is the resolvent, and RV of xi of xy is the kernel of the resolvent. Okay, so there are sort of two points. What we're going to do is to first apply this program in the case of zero potential, so as to see how things work for the flat case. And then we'll look at what modifications have to be done to treat the case of a non-zero potential. And these modifications are not so important. And the fact that we deal first with the zero potential case will make notations much simpler and will make everything more transparent. Okay? So our plan is to do this for the flat case, and then turn on the potential V and try to understand the solutions of this ODE. Any questions?
Could you maybe say again why the f? Because now you apply the operator to the f, so it's the f is probably not the same as f as before, right? So
right. So here, you mean this f here?
yes.
Yes. So okay. Yes. Thank you for your question. So yeah, that's yet another f. It's just saying that if y and x are different, then the right-hand side is 0 here, and you're just trying to understand solutions of this ODE. And this f is maybe a g. I mean, it's just meant to say that,
Okay, all
right? You just want to understand the ODE.
Mm-hmm.
Yeah. Okay, so the case V equals 0. So in this case, we're looking at the operator minus dx squared. And what we are going to do is to write this as the integral of lambda dE lambda. But of course, we already know the answer. The answer is going to be provided by the Fourier transform, which achieves that if you write it in the right way. So we want to apply Stone's formula. And to apply Stone's formula, we need to write the resolvent of minus dx squared. So what is this resolvent doing? It's doing minus dx squared right, minus lambda applied to the resolvent RV. So that's the resolvent at frequency lambda of xy. Okay, so this is rather the kernel of the resolvent. This should be delta of x minus y. And here, so lambda is a complex number, and square root of lambda is xc plus I eta. And so the sort of the difficult case is when the real part of lambda is positive, because minus dx squared has positive spectrum. And so this means that xc will be positive. Or at least we can choose xc positive. And that's one of the determinations of square root of lambda. And we take eta to be positive, which means that we are going to converge the real axis by the upper half plane. Okay, so it's very easy to solve this equation here. So this equation, it's very easy because if x and y are different, then we're just looking at a solution of minus dx squared minus lambda applied to a function equals 0. And we know the solutions are given by complex exponentials. You have a complex exponential for x different from y, and at x equals y, you need to match the left-hand side and the right-hand side so as to get this delta as a result. So delta is the jump in the first derivative, because on the left-hand side you have dx squared. Okay, so that's a computation that you can do, and what you find is that r, so there is no v here, it's r0. R0 so let me get the convention right. Right. R0 of lambda of xy is e to the I xi plus I eta x minus y if x minus y is positive, and same thing with a negative sign if x minus y is negative. Right, so if I draw the graph, that's the graph. There is y, and then you have so there is some decay away from y, and here there is a jump, so maybe it's like that, and there's a jump in the first derivative, something like that. Right, so this gives the delta. I hope that's vaguely helpful. Okay, so it's easy to compute what the resolvent is, and I think it's correct, modulo perhaps some sign errors. And then you can compute the limit as eta goes to 0 of r naught of lambda of xy. And what you find is 1 over 2 ixc e to the ixc. And here you have the minimum of xy minus the maximum of xy. And so this thing is R0 of lambda plus I naught of xy. And obviously you have a similar computation for R0 of lambda minus I naught of xy, which gives the same thing, 1 over 2 ixc, except you flip the sign here in the exponent.
Your question?
Yes.
So can you comment on the fact that you defined the resolvent with lambda positive, but now you're taking so imaginary part positive, but now you're taking the limit from negative imaginary?
Oh, here you mean?
Right.
Oh yeah, so here you need to redo the computation. So the computation we did was for this case.
I see. So you do separately. So okay.
Yeah, and you have
There
a...
are two branches. I thought that you choose a branch, but
No, so the computation is in this case, and then
okay.
There is a symmetric computation which takes care of this case. Yeah. Okay, so I should erase a little bit. So how can I erase without making a mess? I'm not sure. So, okay, I have to erase everything. But we have these two formulas, which once again, are straightforward computations. I mean, it's complicated, but, there is nothing clever. Okay, so now we can apply Stone's formula, which gives dE lambda is 1 over 2 pi I RV lambda plus I naught minus, or R0 I should say, R0 of lambda minus I naught. Which, if you use the formulas that we just wrote, gives C over Xc e to the I Xc x minus y minus e to the minus ixc x minus y. D lambda. And so if you unpack this, you get the classical formula that dE lambda, if I apply it to a function f, so I need to integrate in the y variable. Integrating in the y variable is going to be the same as taking the Fourier transform. Sorry, here xi, there is no xi. Xi is square root of lambda, right? Right, so this is the same as c over xi. Integrating in y is taking the Fourier transform, so I get f hat of xi ei xi x. This is a plus here, plus f hat of minus xi. So if you project on the frequency lambda, which is xi squared, right? You have, and there's d lambda here. You get two contributions, one from the frequency plus xi and one from the frequency minus xi. And then since lambda is xi squared, there is this 1 over xi that comes from the Jacobian of the change of variable.
The c is multiplicative in front of the variable, right?
Sorry?
C of xi just factors out to.
Oh, c, yeah. That's just.
Parentheses in this.
Oh, yes, here. Thank you. Yes, and c is just because I don't want to keep track of constants. Okay, very good. So. Well, it's sort of, if you want, it's like if I look at 1 over lambda plus I epsilon, as epsilon goes to 0, it has a limit in the sense of distribution. So in the sense of distribution, there is going to be it's going to be principal value of 1 over lambda plus constant times the delta function at 0, right? So it's a bit the same that's happening. I mean, it's even exactly the same because if you look at the problem in the right coordinates, the operator becomes a multiplication operator, and then it's exactly these sort of things that you're looking at. So the limit, there is always a meaning in the sense of distribution, and if you subtract 1 over lambda minus I epsilon, only the delta remains. Yeah. Is it helpful? Okay. So now let's move on to the case of a non-zero potential. Okay, and so I guess what we learned, what we need to understand, in addition to the zero potential case, is just how solutions of the ODE with the potential behave, and that's called Yost solutions. So Yost solutions is a particular basis of solutions of the problem minus dx squared plus v f equals xc squared f. Okay, so for now we take c to be real for simplicity. But to do the whole argument, you need to allow for complex c, and there are a few modifications here and there. Okay, so your solutions, they solve this ODE, and you might say, well, it's just a, linear second-order ODE. What can happen? And actually, the main difficulty to understand is the behavior as xc goes to 0, because as long as xc is positive, then the equation has an oscillatory behavior. If you set v to 0, for instance, so far away from the origin. But if xc goes to 0, you lose these oscillations, and new things happen. So it's sort of a singular limit. And the main problem is to understand, what happens when xc goes to 0. So the Yost solutions, they solve this equation, and they have the following boundary condition. So there is one which is called f plus, which is such that f plus of xc is equivalent to eixc as x goes to infinity. And there is one which is called f minus, which is equivalent to e to the minus ixc as x goes to minus infinity. So obviously that's just sign conventions, but what matters is that if I were to draw a picture, so that's v. So v is a potential, that's x. And then if you look at f plus, you prescribe a certain oscillatory behavior, so that's f plus. You prescribe a certain oscillatory behavior at plus infinity, and then you prolong the solution to the left, and you see what happens when it crosses the potential, right? Or in physical terms, it's like a wave which is propagating in the absence of a potential, and when it sees the potential, something happens. So the important thing is given by the transmission and reflection coefficients. So here is the lemma. So if I look at f plus, so I'm going to write the lemma and then explain. F plus of xc, it's 1 over t of xc, f minus of x minus xc, plus r minus of xc divided by t of xc, f minus of xc. So this r is known as the reflection coefficients, and this t is known as the transmission. I will explain shortly what this terminology is about. Okay, so what are we doing here? So f plus, once again, it's defined to the right of the potential. So f plus is defined to the right of the potential. And what I should say, of course, is that f plus of xc and f plus of x minus xc, so f plus of xc and f plus of x minus xc form a basis of the set of solutions of this ODE. Right? It's just because it's a dimension 2 space, and these two are linearly independent, so they form a basis of the set of solutions.
So Pierre, are you assuming that V is even in X?
No, V doesn't have to be even. And I haven't said anything about regularity. We assume that V is, say, in the Schwartz class, but everything would work if we were assuming that it's in L1 with a weight. So you need this. But V doesn't have to be even. There are simplifications when it is even. Yes, so what this equality is about, it's telling you if on the right you look like F plus, then on the left of the potential you want to decompose F plus into a sum of the two elements of the basis, F minus, and the coefficients are given in this manner. So written like that, it doesn't seem to be the most natural way of writing things, but it's this T and R are natural objects. And what's important is that the so-called scattering matrix S of Xi, which is T of Xi, R plus of Xi, R minus of Xi, T of Xi. So this scattering matrix is unitary. And furthermore, T of minus Xi equals T of Xi bar. Okay, the fact that you have such an and there is a similar equality if you put F minus on the left-hand side. So if you decompose F minus in terms of F plus, I don't write it, and that's where the R plus coefficient appears. Right, so the fact that this equality holds is just due to the fact that f minus of x xi, f minus of x minus xi is a basis, okay? So what's important is this relation on the coefficients. First, the unitarity of this matrix, and then these things about bar. But this can essentially all be, so proof, more or less, you need to use variants of the following argument. If I look at W of, say, f plus of x xi, f plus of x minus xi, so the Wronskian, it's independent of x, of course. And so you can evaluate it at plus infinity, at minus infinity. And you can do that with f plus, f minus, f plus, many combinations. And if you try them all, you get these relations on the transmission and reflection coefficients. Okay. So now let me draw the picture that physicists draw, which is always sort of half mysterious to me, but also half helpful. So I'm going to draw it. Okay, so the physicist picture. Here is the physicist picture. So, okay, so that's space. We have our potential, like that. And say you have an incoming wave, which is F minus of, maybe I should rewrite. So the formula that I just wrote, if you multiply out by T of xi, what you get is that T of xi times F plus of xi is F minus of x minus xi plus R minus of xi divided by T of xi. No, sorry, I multiplied out by T of xi, so there is no T of xi. F minus of x minus of x xi. Right. So the incoming wave is this one, so that's the incoming. And that's F minus of x minus xi. It's hitting this potential, and then you have part of the wave that goes through, and that's the transmitted wave. So it's F plus of xc with the transmission coefficient T of xi. And part of the wave bounces back, and so that's the reflected wave. And it's this one, R minus of xi, F minus of xc. Okay, so you see this equality says that so it's right, that this transmitted wave can be seen as the sum of the incoming and the reflected wave. And furthermore, right, there is the conservation of energy. So conservation of energy tells you that the energy of the incoming wave is distributed between the reflected and the transmitted wave. So that results in T of xi squared plus R minus of xi squared equals 1. So it's like conservation of energy in this picture, and it's part of the statement that the scattering matrix is unitary. So I think it's nice to have this, but I have no clue how to make it rigorous or how to think of it rigorously. If you guys have a suggestion, I'd be happy. Okay, so in any case, that's, I think, a nice way of thinking of this reflection and transmission coefficients. Okay, so as I was saying earlier, what matters is, or at least one important element, is the behavior of these reflection transmission coefficients as t goes to 0. And so there are essentially two possibilities that go by the name of generic and exceptional potentials, and I will discuss these now, unless you have questions. Okay, so lemma. So the following assertions are equivalent. So first statement, t of 0. So t, remember, it's the transmission coefficient. T of 0 equals 0. And the reflections r plus minus of 0 equals minus 1. That's the first statement. And when writing this down, of course, you're going to tell me how do you define t and r at 0 frequency. And indeed, there is a problem because the f plus and f minus, if I let xi go to 0, they don't constitute a basis of solutions anymore, because as xi goes to 0, both f plus of x, there is just one f plus of x0, which is 1 on the, which is going to 1 as x goes to infinity. And so, you know, it's not a basis anymore. And so the lemma that I stated doesn't really make sense if xi is 0. But there is a way to show that these have limits. So t and r have limits as xi goes to 0. It's not hard to see, and okay, but I'm omitting it. So first statement, t is 0 and r is minus 1. Second statement, there is no resonance at 0. What is a resonance? I.e., there doesn't exist a bounded non-zero solution of minus dx squared plus v phi equals 0. You know, so if either, hence both of these assertions are true, if these are true, V is called a generic, and otherwise it's called exceptional.
Are you assuming that V is positive or something like that?
No. V is just real valued. That's it. Okay, so maybe two remarks. So remark one is that if you take V equals 0, then just the function identically equal to 1 is a resonance. So the zero potential is exceptional with this definition because it has bounded non-zero solution of dx squared f equals 0. Okay. And remark two, where does this terminology come from? Is it indeed the case that generically a potential is generic, if you see what I mean, right? So if you take a generic potential, why is there no resonance? So let me try to argue that this is the case. So let's say the potential is compactly supported, right? The potential is compactly supported. So, and we look at the equation minus dx squared plus v applied to f equals 0. So on the support of the potential, you know, we cannot say exactly what happens. But on the right of the spectrum of the potential, a basis of solution of dx squared f equals 0 is provided by f equals 1 and f equals x. Right? That's clearly a basis of solutions. And on the left of the support of the potential, same thing, f equals 1, f equals x, provide a basis of solutions. So now, what does it mean that the potential is exceptional? So what does it mean that there is a resonance? It means that if you solve the equation with f equals 1 to the right of the potential, okay, then you solve through the potential, and then you see how it emerges on the left. So on the left, it's going to be a linear combination of f equals 1 and f equals x. And the only way that this thing is bounded is if the component on f equals x equals 0, which of course in general is not the case, right? And even generically, if you put f equals 1 on the left, what comes out on the right, what comes out on the left is a linear combination, a non-trivial linear combination of 1 and x. And therefore, the thing is not bounded, and you don't have a resonance. So this terminology is indeed meaningful. Generically, a potential is generic. Right? Could you follow the discussion? Please let me know if I wasn't clear.
So just a question, because what you said makes perfect sense for positive potential, but is it not the case that if you have a deep potential well, so negative and deep enough, and then you'll always have bound states, and therefore will not be generic?
Oh, so here, this whole discussion is for... Right. So the bound state will happen at a specific frequency, right? So you need to add here a lambda, and you pick the lambda exactly so that it connects the stable manifolds on the right and on the left of the potential. But for most lambda, if you decay exponentially on the right, then you will blow up on the left. So there will be an exceptional lambda that will give you an eigenfunction or an eigenvalue. But most of this discussion was not, and this would be if you take lambda to be positive, right? But most of this discussion is for lambda negative, and maybe letting lambda go to 0, in which case you have oscillatory behaviors on both ends. Does it make sense?
So that would be okay. So that would be some fine tuning to have a 0 eigenvalue or something like that. That would be.
Well, it's not. You cannot have a 0 eigenvalue, right? Because for the free solution, it's going to be either 1 or x at infinity. So you cannot have an eigenfunction in L2. That's not possible. The best you can have.
If V is negative, can you not? I mean, if V is negative and V cannot, can you not?
No, because as soon as you exit the support of V, let's say V is compactly supported for simplicity,
okay, sure.
as soon as you exit the, right?
So you need tails for what I'm saying.
So if you look at a 0 eigenvalue, so lambda equals 0, right? As soon as you're away from the support of V, then your function is either constant or linearly growing. So it's never going to be in L2, but it can be in L infinity if it is properly tuned, which happens exceptionally.
Well, it could be constant equals 0. Okay, I'm just okay. I mean,
but if it's 0,
so it is.
Yeah.
You're assuming compactly supported.
Well, if it's not, then you need to have a small perturbation argument that works if V is decaying sufficiently fast. And I think sufficiently fast is faster than 1 over x squared. Any other questions? Okay, so maybe let me not give a proof, but a caricature of a proof. So we start from the formula T of Xi f plus of xc equals f minus of x minus xc plus r minus of xc f minus of xc. Okay, and we let xc go to 0. So as xc goes to 0, as xc goes to 0, okay, so which one do we want to assume? So t of xc goes to t of 0, that's for sure. F plus of xc goes to 1, at least for x much bigger than 1. And this also goes to 1 for x much less than 1. And same here. That's just by definition of the Yost solutions. Okay. So let's see. Okay, how do I want to put it? Right. So if, say, let's do the contrapositive. So if t of 0 is not 0, say, then on the left-hand side, you have a function which is bounded for x much bigger than 1. And on the right-hand side, you also have a function which is bounded, but this time for x much less than 1. So you see that in this limit, what you get is a resonance. So it means the limit, or let's just write it f plus of x 0 is a resonance. Okay, and you have a similar argument in the case where t of 0 is 0.
Could you explain what you mean by x much less than 1? Do you mean x is very negative, or is it just very small?
Oh, sorry. Yes, it's rather minus 1. So yeah, it's a bit of a not a great notation. Yeah, x very negative. So essentially, just thinking of the case where v is compactly supported, then you just need to be outside of the support. And otherwise, there is just a small perturbative argument that you need to do. Okay, so that's what generic versus exceptional potentials mean. And the fact that, for instance, t is 0 or not at 0 will have very remarkable consequences on the Schrödinger group. So it's not just technical consideration. It will be dynamically very relevant, and we'll come back to that next time. Okay, so now we have a good understanding of Yost solutions. So we have a good understanding of a good basis of solutions of the ODE. Now you can run the same argument as in the flat case v equals 0 and get to define the distorted Fourier transform, which I will now do.
Pierre, can you say again what do you mean by, what is the definition of a distorted Fourier transform when v was 0? So that was this
Oh, yeah.
measure?
Right, no, so when v is 0 is the regular, or maybe sometimes I say the flat Fourier transform, and it's distorted when you add a potential. And that's what we're going to define now.
Okay.
Okay, so distorted Fourier transform. Okay, so in the flat case for v equals 0, of course the Fourier transform is defined through the complex exponential EIXC. And in the distorted case, this becomes psi of xc, which is defined as follows: 1 over square root of 2 pi times f plus of xc times t of xc for xc greater than or equal to 0, and f minus of xc x minus xc, sorry, times t of minus xc if xc is less than or equal to 0. And then you define f tilde, so I denote it by a tilde. So a hat is for the flat case, and tilde is when you add a potential. F tilde of xc is the integral of f of x psi of xc bar dx. Okay, and you should really think of this as the analog of the flat Fourier transform, except that now it's adapted to the case where there is a potential. So, okay, there are several possible definitions. Just like in the case of the flat Fourier transform, you can use the complex exponentials as a basis. So it means at frequency. So if you look at the eigenvalue xc squared of minus dx squared, the eigenvalue xc squared of minus dx squared has a basis which consists of e ixc and e minus ixc. But you could just as well choose, sinus of xc and cosine of xc as a basis. Same thing here. You have several possible bases, but this one is good. Maybe I'll try to explain why. So the theorem. So you proceed just like in the flat case. You apply the spectral theorem and you use Stone's formula. And the theorem that you get is that. So this. Tilde operator, let's call f tilde the distorted Fourier transform. So it's going to be unitary on L2. I should say L2, so projected on the continuous spectrum. But that's more of a technicality, but you need to exclude possible eigenvalues. So, okay, f tilde is unitary. And that's just because F tilde, if you want, is the change of basis that diagonalizes the operator, and since the operator is self-adjoint, the change of basis is unitary. Or to put it differently, it's because of the projectors that come up in the spectral theorem formulation. Okay, so F tilde also maps L1 function to continuous functions that decay at infinity. So this is very reminiscent of the flat Fourier transform, right? But now there are differences. In particular, if you're in the generic case, so in the generic case, if you look at F tilde of 0, this is 0 if F is in L1, which of course is not the case in the flat case. That's different from the regular Fourier transform, right? For the regular Fourier transform, a function does not necessarily have Fourier transform 0 at frequency 0. But in the generic case, it is the case simply because if you look at this formula and you plug in xi equals 0, what you get is t of 0. And when in the generic case, t of 0 is 0, so what you get is that the function psi of x0 is 0. So there is just no way that f tilde 0 is something else. Okay. And finally, what we were, looking for, f tilde diagonalizes minus dx squared plus v. In other words, if I look at minus dx squared plus v, I can write it as f tilde inverse times xi squared times f tilde. And so for us, that's very important because it gives us a way of decomposing a solution of the linearized problem around the soliton and of seeing, at which speed its various components oscillate. Okay, and the proof of this theorem, as I was saying, it's just the spectral theorem and more specifically Stone's formula, along with what we discussed about Yost functions. Okay, I think I will stop here for today. Next time we will see applications of these ideas to the stability of solitons. Yes, that's going to be the plan. Did you guys have any questions?
Yes, I have a couple of questions. So the first one is, last statement that you wrote is, as well as for the first, it refers to the absolutely continuous part of L2, right?
Mm-hmm.
So in order to have this sort of diagonalization, you have to take into account the eigenvalues, right?
Yes.
So one can do that. Okay. And so the other question is, maybe you partially answered before. So what is the exact, an exact, let's say, hypothesis on potential in order for this theorem to hold?
Right, so what you need is xv to be in L1. xv to be in L1. And essentially, here is the reason why. So you look at minus dx squared plus v. Right, minus dx squared plus v. Okay, and all of this is going to work when the dx squared part will be, dominant over the potential part. So now, sort of scaling-wise, what does it mean? Well, minus dx squared is like 2 derivatives of x, obviously, and it scales like 1 over x squared, right? Minus dx squared. It scales like 1 over x squared. So if v decays faster than 1 over x squared, the minus dx squared part is going to take over, and otherwise, perhaps not. So one way of seeing that v decays faster than 1 over x squared is to ask that the integral of x v dx is finite.